This is the second video in the Art of HF series talking about antenna design this time. In the first video we picked our frequency 11 megahertz and we want to use this frequency to talk from the bottom of the UK up to the top, 1,000-kilometer link. So we need to build an antenna, but how high should the antenna be, which direction should the antenna be facing, and what other considerations should we use for planning this antenna? The first one is the height. We know the frequency, which means we know the wavelength. So to calculate the wavelength using our pocket calculator, we can take 300 and divide it by the frequency in megahertz, and that gives us a 27 meter wavelength. So that's quite a long wavelength because it is a low frequency. For a HF dipole, which is the type of antenna we're going to build, we need the half wavelength. So the quick way to do that is 150 over the frequency in megahertz. So this is half the amount. And this time we get something that's a bit more achievable if you're limited on space. So a half wavelength is 13.6 meters. But let's say we don't have masts that can go that high, and we haven't got trees that we can use that are that high. So what's our next best option? Well, it's the quarter wavelength. They're all multiples. So the quarter wavelength, again, it's a multiplier of the full wavelength. So 75 in this case divided by the frequency in megahertz gives us something much more practical, 6.8 meters. We can do this. So 6.8 meters is going to be our target height. Now the height that you build your antenna off the ground will affect its propagation. It will affect the antenna pattern, which will change as the dipole goes up or down, and you will get a different takeoff angle. So when people talk about takeoff angle, they're talking about the angle at which your RF is striking the ionosphere. So we're going to go with a quarter wavelength of 6.8 meters, and once we've got this link planned, we're going to play with this height and go up and down and see what it looks like, because we have the luxury of doing that here. The frequency is 11, and the power, just to make our lives a bit harder, we're going to dial down the power to 5 watts. So 5 watts, not a great deal of power to talk 1,000 kilometers. However, this is HF, it's different. So height has been picked and the power we've put low. The feeder, you're going to be running a feeder up this mast to feed the dipole at the middle, and so we know the feeder is going to be at least 7 meters long and probably some more. So if we're talking HF, we're probably talking something like RG58, which as you go longer increases in loss. So let's say it's a 50 meter coax, it's about 2 decibels of loss at this frequency. If you've got some of the more expensive low loss coax, it's about 1 decibel of loss. If you're not sure, just put in 1 in this box here. You need to simulate some loss. Notice the efficiency is dropping as the coax gets longer. You don't want a really long coiled up coax, you're just throwing away power. So keep that coax short if you can. If you can do this with a 15 meter coax, the efficiency is now 67%. So keep that coax short if you can, even though the loss is low with HF. Right, antenna menu. We said we were going to do a dipole. We have a list of different antennas we can choose from. Horizontal dipole is the one we want here. The gain for a horizontal dipole is 2.15 on a good day, so this is the optimal gain for this design. In the real world, there's inefficiencies in our antenna design, and so you could play it safe and say that it's only 1 dBi gain, for example. The azimuth, we will leave the azimuth as 0 for now, and just run this model as it is just to have a look, and then we will come back to the azimuth and the height. So remember, we're trying to hit the top of Scotland here, so I'm hovering my mouse and I'm getting an S2 signal here, so pretty weak, and you can actually see the pattern of the dipoles. The nulls on this dipole are at either end of where the dipole terminates. So if this dipole is orientated north, then that means the legs are pointing east and west like this, and the RF power is heading north and south towards Spain. If we were to rotate this dipole the wrong way, at 1,000 kilometers, we would suffer for that, and we would actually have an even weaker signal, an S1 signal now, whereas we've actually improved our signal over towards Germany here. So you can get away with a badly orientated dipole at short distances, but it will make a big difference at long distances. So let's find out the correct azimuth here, and it's about 9 degrees grid north. So we're putting in 9 degrees for the azimuth, and we now have orientated our dipole correctly towards our objective. So the two legs would be going left and right, like so. Let's play with the height that we mentioned earlier. So we set the height at a quarter wavelength for this frequency, but let's say we're using 8-meter masts and we just hoist it up right up to the top and see how that compares. So we're going a little bit higher now. It should be a slightly gentler takeoff angle, and we can see we've actually extended coverage into the North Sea there, so we actually got further. So that follows the logic that big is better when you're putting up a HF dipole. Not always the case. You can have a perfectly good HF link with a dipole that's close to the ground, but it depends on the frequency, it depends on the time of the day. So that's the height done, and despite only having 5 watts of power, we're able to get an S2 signal up here at the top of Scotland. So let's crank that power up and see how it compares, and see if we can spot any hotspots. So there's one. There is a band of what looks like S4, so an S4 signal there at the top of Scotland, and it covers our objective here. So we're happy with that, and that's a good configuration there for a HF dipole, 8 meters above the ground, 10 watts of power, and we've budgeted for the feeder, and we've put in some compensation for and slight inefficiencies on the antenna, because we might have made this from copper wire, for example, which has been cut to length. So that is a crash course in how to design an antenna using CloudRF, and in the next video we will go into long-range forecasting for how to plan ahead many weeks into the future.